Okay, so we've seen that our particles can move faster than light, and I've claimed that this is a problem because it spoils relativistic causality. That's what I'd like to explain now. So what is relativistic causality? Well, causality is the statement that causes come before effects. So let me give you an example. Let's imagine you're sitting in your room and a bomb is blown up in the room. What will happen is that bomb will explode. It will produce a pressure wave. That pressure wave will move outwards. It will hit the windows in the room and those will be shattered. So the cause was the bomb. The effect was the shattering of the windows. Now, if you see a bomb explode and a little bit later the windows shatter, that's perfectly consistent with causality. The cause came before the effect. What we don't want, it wouldn't make sense if the windows suddenly shatter because somehow they know that in 1 second time, a bomb is going to blow up. It doesn't make sense for the effects to come before the causes. We must first have the cause and then the effect. We want to look at what it means to have causes coming before the effects, but in the context of special relativity. Okay, so we need to now talk a little bit about relativity. So let's imagine, I'm going to imagine I've got two reference frames. So here's the first reference frame. It has a time axis t, and it has a space axis x. And there's a second frame with a time axis t prime and a space axis x prime. So let's call this frame O and this frame O prime. What is the relation between the two? O prime moves away from O, and it moves along the positive x-axis. So if you looked at the origin of O and O prime, they're not moving in the y direction, so y is equal to y prime. They're not moving in the z direction, so z is equal to z prime. So I'm not showing the y and z directions now, but it is moving in the x direction. So the origin of O prime, as time goes on, gets further and further away from the origin of O. Now, I want to write down what is the relation between the coordinates as measured in the O frame and the coordinates as measured in the O prime frame. And this is the relation. So T prime is equal to cosh, the hyperbolic cos, so cosh phi times by t plus sinh phi, some of you say shine, I'll say sinh phi times by x. X prime is equal to cosh phi times by x plus sinh phi times by t. And as we said, y prime is equal to y and z prime is equal to z. Now, let's just talk a little bit about this relation between the two. Of course, this is a Lorentz transformation, okay? So what I've written down here really is a Lorentz transformation. Now, you may be more used to writing Lorentz transformations referring to the velocity of the particle. Here I'm using this quantity phi, this parameter phi, and this is known as the rapidity. Okay, it's a particularly useful way of parameterizing Lorentz transformations, but I should tell you how it's related to the velocity. And the relationship is that v is equal to the tanh of the rapidity, the tanh of phi. Now, for this one formula, and for this one formula only, I'm going to put the speed of light back in. If I put the speed of light back in, it's v divided by c is equal to tanh phi. So let's first of all talk about this equation. Why is this a natural, why is the rapidity a natural variable to use? Well, if we plot tanh phi versus phi, so I'm sure you know this, but let's just discuss it. If we plot tanh phi versus phi, I think you know at the origin it behaves linearly, but as you take phi to infinity, tanh phi asymptotes to the value of 1. And as you take phi to minus infinity, tanh phi asymptotes to the value of minus 1. So that means whatever the value of phi is, v over c at its biggest is 1, and at smallest, it tends to minus 1. So that means you can never have velocities which are faster than the speed of light. That's naturally built into this parameterization in terms of rapidity. There's many other things we could say, but maybe that's enough for now. And of course, the other thing which is nice is I would never remember the usual Lorentz transformations, but this is such an easy transformation to remember. So when you work in terms of the rapidity, it's much easier to write the formulas. Okay, but now let's try to see how we would rewrite our Lorentz transformation back in terms of the velocity v again. And for that, we just need to do a little bit of hyperbolic geometry. So I wonder if you remember your hyperbolic geometry. If you remember, cosh squared phi minus sinh squared phi is equal to 1. You should be able to derive that. If you can't, look it up. Now let's divide by cosh squared. So if we divide both sides by cosh squared, we get 1 minus tanh squared phi is equal to 1 over cosh squared phi. And that's a very easy equation to solve. Well, cosh phi is nothing but 1 over the square root of 1 minus tanh squared phi. Notice I've taken the plus square root. You might wonder how I know that I can do that. Well, I can do that because cosh is always positive. And this is equal to 1 over 1 minus v squared square rooted. And just remember, this would have been v squared over c squared if c was in the game. I put c to 1, so I'm not going to put c back in. But you remember the 1 over 1 minus v squared over c squared factors that used to appear everywhere. And then when we look at sinh phi, well, the easy way to get sinh phi, this is just tanh phi times cosh phi. So I just need to multiply the cosh phi by tanh phi. And tanh phi is just v. So this is just v over the square root of 1 minus v squared. Good. So that's how you would express things back in terms of velocity. Okay, very good. Now I want to draw on the same plane. I want to draw the O reference frame. So here is t, there is x, and I would also like to put on this plot the t prime and x prime axes. So let's imagine I'm drawing all of this at time t is equal to 0, when the origin of O and O prime was at the same point. Now, what is the t-axis? So the t-axis is the line x equals to 0. That's what that line is, x is equal to 0. So if we want the t prime axis, we need to look at the equation x prime is equal to 0. Well, we've got x prime over here. It's just cosh phi x plus sinh phi times by t. So we'll get naught is equal to cosh phi x plus sinh phi times by t. And if we solve, what is t equal to? T is equal to minus 1 over the tangent of phi times by x. So we have a line with a negative slope. So negative slope. And what else do we know about the slope? Well, tangent is always less than 1. So 1 over tangent will be greater than 1. So it's a negative slope of magnitude which is greater than 1. So a very steep line. So if we draw the t prime axis, this is what the t prime axis will look like. There is t prime. Okay? Very good. Now, if you do exactly the same exercise, and I'm going to let you do it, you can work out where the x prime axis is. So what is the x-axis? The x-axis is the line t is equal to 0. So you would say t prime is equal to 0, and that would tell you what the x prime axis is. So here is the x prime axis. Okay, good. Okay, let me just clear up a bit of space. So I hope that you understood exactly what we did there. We've got the t prime and the x prime axes, and let's talk about what does this mean. Now, I want to draw some lines of all the same time t prime. So of course the x prime axis, all points on those lines have the same value for t prime. But if I draw any line parallel to the x prime axis, all of these are lines, sorry, my drawing's not great, but these are all lines of equal t prime. So for all of these lines, you would say these are all happening at the same t prime. Okay? Now I want to show you what happens if cause and effect are space-like separated. So let's now have the cause of something. So here is the cause. And let's imagine I am in the O-primed frame. Okay, there's the cause. I'll label it C. Okay, cause C. And let me say, what is the effect? Well, in this T prime frame, I'm going to make sure that the effect comes after the cause. Okay, so I will put the effect over here. That's the effect E. Now notice something. So E comes after C in the O prime frame, but here's an important point. C and E are space-like separated. Okay? So this is a situation where that effect could only happen if, say, the bomb that blew up at the cause at C produced particles that traveled faster than light. Okay? So this is exactly a situation that we talk about where particles travel faster than light. Why is that? Well, because you can see from this line over here that light couldn't possibly travel from C to E. E is too, it's got too big an X prime value for light to be able to get there. Now I want you to look at things in the O frame. In the O frame. So in the O frame, what's going on? Well, here is the cause happening at this time, and the effect happens at this time over here. So in the O frame, the effect comes before the cause. And the claim is, if the effect is space-like separated from the cause, then there is some Lorentz frame in which the effect happens before the cause, so you spoil causality. Okay? So if the effect is space-like separated from the cause, then even if the effect comes after the cause in some Lorentz frame, you'll be able to see the effect coming before the cause. And this is what this diagram illustrates. So, if you want to preserve causality, so that means in every single Lorentz frame, the effect must happen after the cause. So that's what I mean by these three words. So to preserve causality, I mean in every single Lorentz frame, the effect comes after the cause. To preserve causality, the effect must be time-like separated from the cause. So maybe just to labor the point, if this is T and that's X, let's say this is where the cause happens. Here are the world lines of light. The only place where you can have an effect is somewhere between these two lines. It must be time-like separated from C. In particular, you cannot have any effect happening in this region. There must be no effect. No effect. Okay? So whatever you do at the origin, you should not affect these red regions. Now, our particle could travel faster than light, so we let it go at the origin. It could get to these red regions, and that means it spoils relativistic causality. That is the problem with our single particle theory.